Today I brought you some of them. So today I'm going to talk about basically learning-based pipelines, right? Or in more sophisticated terms, combinatorial optimization of augmented learning in contextual multi-stage decision-making, right? So basically online problems with some uncertainty. So that should work. Before we start, I didn't do all of this alone, right? So there are many people who contributed to this. Thibaut is in the room, Axel Parmentier from École de Port, James Harrison from Google, Walter from Twente, and many of our students who had to suffer all the coding from the ideas that we had, right? So if you like what we're seeing today, it's all those guys' faults. If you don't like what you're seeing today, it's my fault, right? Then you can complain afterwards. But let's get to the topics. So I think what we see over the last years is that many of the planning problems that we face that have been static 10 years ago are these days dynamic, right? Just think about vehicle routing. It was day ahead planning 10 years ago. Now you have Amazon, e-commerce, same-day delivery. So you end up more and more in settings that require fast decision-making under uncertainty, and you're ending up with multi-stage problems. And with this, we also see more dynamic algorithms, right? So I could put 20 more headlines. I just selected some. You see more end-to-end learning, predicts and optimize, smart predict and optimize, reinforcement learning here, reinforcement learning there, structured learning here, structured learning there, right? So there's a huge interest in somehow leveraging learning to create better algorithms for those contextual multi-stage decision-making problems. And this is what I want to talk about today. So the last times I talked about it, I always selected one topic and presented it, and then people had questions, and I always started answering with, yeah, that's an interesting question. We did it in a different paper. That's an interesting question. We did it in a different paper. So today we make a little experiment. I try to condense 5 or 6 papers in 50 minutes, which is at the same time the apology for not finishing on time. Notation maybe being inconsistent and skipping some details, right? But I pointed to papers everywhere if you want to see the details, or I will also be around today and tomorrow if you directly want to chat about it. If you get lost halfway, just interrupt me, right? That would also be a good apology for me to say I was just over time because there was this guy always asking questions halfway. Okay, so let's get started. So there's one blog on structured learning pipelines and one blog on deep reinforcement learning-based pipelines, right? So I'll start with the structured learning ones with an example on which we worked in the realm of this EUROMeetsNeurIPS dynamic vehicle routing competition last year. So there's a paper that has recently been published. If you want to see the details, I'll first give you an idea of the problem that was proposed in this competition, right? It was basically a dynamic routing problem where you had an unlimited fleet of vehicles. You had requests arriving over time. Demand was uncertain, time windows and service time as well. And then the decisions that you have to make is you have to dispatch vehicles at fixed points in time to serve those requests, right? So basically in technical terms from practice, it would be dispatching waves. So you collect requests for 1 hour, then you take a decision who to serve, you collect more requests and so on and so on. Once you dispatch something, you cannot modify it. It's not mobility on demand, it's logistics. So it's something like this, right? So you have requests arriving with some time windows. That is your first dispatching wave. Then you take a decision, then your next request arrives. It's the next wave, each having a time window. You take a decision again. At some point in time, horizon is over, and then you're done. Your objective is to minimize total travel time or some cost factor on the routes that you're deciding on. And you have to serve all requests, right? So worst case, you delay a request too long. At some point, you have to send a vehicle for one request, which will have a high cost for just delivering one request. So a bit more technical, if you want to model that, I mean, that's can be modeled as an MVP. So we'll talk a little bit about states, transitions, decisions, and policies, right? And then the question is, how do we learn that policy? In the end, what we have is we have some time horizon from 0 to a finite end. We have requests arriving continuously over time. And then still what we do is we discretize our time horizon into epochs. Each epoch relating to one dispatching wave. So we will collect the requests, then epoch is over, we take a decision what to release, how to route, and collect new requests. So that's what we're doing. which makes the system state super simple, right? Because the system state in an epoch can just be described by the request set that we collect in this epoch from the request set right at the time. Then we have a feasible decision, which is basically a set of routes related to those requests. And there we make a little distinction that we say, okay, there's something which is called a must dispatch request. So if you remember the last slide, the requests have time windows. So the time window is tight. Since you have a constraint to serve all customers, you need to serve it in some epoch. And this latest epoch where you have to serve it makes a request a must dispatching request. So decision there is simple, you just serve. Then for everything that you decide on here, you should be feasible with respect to time windows and capacity of the vehicles and so on. So conventional routing constraints. So you take your decision, then your system evolves. So you transition from your state in epoch E to the next epoch E prime. And you can do so by just removing the requests that you dispatched and route from the request set that you have. You add the requests that sum up over time in the next epoch, and then you take the next decision. And in this setting, we're just looking for a policy that maps the state space to the decision space, and we want to minimize the expected costs that we save in that problem. Right? So more visual, this is also where the PhD students suffer to make nice animations of what was in my head. It could be something like this, right? You have a depot, you have a fleet, you have customers that arrive in this epoch. 2 of them are must dispatch. So when you decide on your routes, you need to serve them. The others are optional. So the decision could look like this. So you have to serve them. So it might be a smart idea to serve some in the close vicinity. You save some others for later. So those 4 guys will stay in the system. Some new requests arrive. Some of them are must dispatch. Some of them are not. You again decide on routes, some stay in the system, and so on and so on. You assume that epoch 3 is your last epoch. So in the last epoch, everything is must dispatch because this is constrained to serve everybody. So you serve the remaining ones, and then you hope that you did it in a smart way to minimize the cost that you're facing.
So Max, just a quick question.
Sure.
So are the trucks that do routes in one epoch reused later, or you just assume anytime you need to dispatch something there is a truck about it?
There's just one available. So this is actually something we discussed with the referees when we published the paper after the competition, and also something we looked at. Or it's the case it's not super realistic. The fleet size is unlimited. Okay. But you balance it in the way that if you take a super stupid decision, you will send a truck for one request at the end. So you have a very high cost. So you're, by the overall setting, you're implicitly minimizing fleet size. Yeah. But it's a point to discuss here. It was good luck for us because every answer to the referee was the competition designers did it this way.
So link it maybe to that. I guess if the trucks are reused or the same, the fleet is limited, then maybe you want to make the decision epochs flexible.
Yeah, you could. So you could do it. So the methodology I present would still work. Okay, so it doesn't rely on having equidistant intervals on the epochs. And you could also model constraints. If you model constraints, it gets much more dirty on the learning because you need to penalize it in the objective and things get a bit messy, but in theory it's possible. We didn't test it yet because the competition organizers.
I have a strong hint that the competition organizers didn't want to mess up with feasibility issues when doing the competition.
Yeah. We would have liked that, but sorry, all the other teams not. No, I mean, it's a reasonable assumption. Just put a high penalty. Yeah, I agree. Okay, so that's a problem setting. So if you think about this problem, I give it to you and you solve it for me. The easiest thing you can do is you do something like this, right? So you just decompose your problem. You say I dispatch first and then I route, right? And then I do some learning for the dispatching decision. And then there's a routing oracle second stage I do not even care about, and that's it. So nice thing about this is you decompose, right? So you reduce complexity, which is generally something we like. But the bad thing about it is you lose on this end, right? So if you radically decompose, you just hide the problem structure in the routing, which is also your cost oracle from your dispatching decision, right? And that may give you problems on what is the right loss function on this decomposed learning problem or this isolated learning problem. So this is why we didn't went that route, but we didn't went a different route. which is basically the following one. So okay, instead of decomposing, let's think about an integrated way of modeling this problem to keep the structure from the routing problem and not hide it from the predictor. So what you can do is you can reformulate the problem by saying, okay, instead of solving some dispatching problem and then some routing problem, let's just reformulate this problem as a price collecting DRP. Right, so I will just give you a price collecting problem where there's a price on each customer and there is a cost for serving the customers. So then this proposition was an easy one to prove. So you can do it in 5 minutes or read it in the paper. You can say, okay, there will always exist a parameterization of the thetas, which is the prices for the customers, that will trigger my routing algorithm to create a solution that is similar to the optimal solution of the proposed problem. Right, you just need to find the right theta, and unsurprisingly, spoiler alert, a large part of this topic will be on how to find that theta, right? This is where then the learning kicks in. But instead of splitting it, we find a surrogate problem that keeps the structure and still allows us to learn some parameterization that helps us to make a smart decision in the combinatorial layer, right? And here, this problem is just a price collecting here. So that brings us to the main part here, which is the question, okay, how do we find the right price vector, right? And intuitively, if you think about that price vector, okay, that price vector should somehow incur the consequences for later epochs, right? So if you think about it, not in terms of profit prices, but cost pricing, then you want to price how costly it is if you delay that. If that is more costly than putting it on a route in the epoch where you're deciding, you put it on a route, right? So unfortunately, if we want to do that, then we need to have knowledge about future requests, which we don't have, which is where the learning comes in, right? So the question is, how can we predict the right price vector in this setting? And this is where our integrated pipeline kicks in. So the pipeline I'm looking at looks something like this. So I look at a pipeline with a learning layer and a combinatorial layer. So I will pass some state into the learning layer. This learning layer will give me a parameterization for my thetas. This is what I will feed into the instance of my price collecting DRP. I run some algorithm to solve it. I get some routes. And from those routes, I take the information which requests a dispatch, which adjusts the request on the routes. The other ones, I keep them in the system. I execute the routes, transition to the next step. Right, so that's basically what I'm aiming at, which leaves two questions, which is how to learn prices and how to solve the problem. The remaining routing problem. The routing problem, I do it in 10 seconds. Is we basically use Thibault's algorithm with some modifications, right? That was also given to us by the competition organizers. I will ask you afterwards who was one of the competition organizers, and you can make a wild guess. So I will not talk about it today. We made some modifications, but it's a different story, right? And then what we end up with is something that we call a structured learning problem, right? Because what we were given in the setting is some past data. We could sample some data to see how requests revealed over time or the last day, the week before, and so on and so on. So if you have that data, what you can do is you can create a data set that contains some states, and in hindsight, optimal solutions for those states. Right? So basically what we did is we took full information data for a full day, solved the VRP on this, then sliced the solution into the time intervals that we had. And that gave us the tuples that you see here, right? So this is just the requests that arrived in some time interval and the routes triggered for the requests released in the time interval. But this information was retrieved from the full information of the day from which we sliced it. Okay. Yeah.
So here, your theta is kind of, do you want to measure theta as a function of the time and the state, which is your x? Is it like this?
No, the theta, it's just a parameterization of the second layer, so of the optimization layer. And I want to learn the predictor who gives me that parameterization based on anticipated policies from the past.
Is this theta constant?
No.
Yes. So this where I'm thinking like you speed
okay, now I got your question.
So it's more like you have you want to estimate the value of the theta.
Yes, you have a predictor who takes the state and the time as an input, and then you get a parameterization for theta that varies with x and t. Yeah, that's right.
That's where you say that you want to learn a policy in the sense.
Exactly. Yeah. Yeah. Okay. Yeah. So that's what we have, and it would be something like this, right? So you know the structure for those different tuples. And then what we want to do in the training, and I think this is the written answer to your question, right? So we have a predictor phi with some parameterization w, which we learn in the training, that receives the timestamp in the state as an input and outputs the time-dependent theta for the instance that we pass into the combinatorial layer, which is that so. Right? So this is the main idea of what we have. And we want to do that by backpropagation, right? So there will be some loss function. We calculate the gradient over that loss function, and that helps us to converge to a parameterization for phi, which is reasonable. So this is the idea. And this is where we face a structured learning problem, right? So the loss function that I would like to use in this setting, since I'm aiming to imitate anticipative policies, is that I want to get the structure of the solution that I get when I solve the online sliced instances as close as possible to the structure of the full information offline solution from the past, right? And this is what this difference is telling you, just that the G represents the cost part on selecting the dispatch requests, and the H represents the cost part related to the routing, but I was too lazy to put even more sums on that slide and wanted to keep it lean, right? But that is basically the parts from the objectives that we have before. So this is what we have. And this is then what we get when we evaluate the loss, right? So this here is fixed, assume that this is the optimal decision. Then we have phi that gives us some theta. So what we will do is that for the first part, we pass the parameterized instance in the combinatorial layer, solve it, get this solution, and this will trigger a different cost term here than here. So we will see a loss which is greater than 0 until we converge on learning phi such that we get prices that on this first part also gives us a structure that we have fixed in the optimal training science. Right, so that is, I skipped probably 1,000 iterations of backpropagation in between, right? But you will start somewhere here and you want to get here. So this is basically what we do. And the straightforward loss function would be this one. This is my emails. So the problem with this loss function is that if you think about the polyhedron over y, then we get something that is generally very degenerate, right? So trivial solution for that loss function on the last slide would be setting theta to 0. You dispatch 0 requests, you have 0 costs, so you have a 0 loss, but it's pretty much not what you want to reach, right? So what we will do to mitigate this issue is that we will add some Gaussian perturbation precisely here on the theta. And by doing so, we will get a loss function that luckily is smooth convex and has a gradient, which is also great because we want to do backpropagation on some gradient, right? So why do we need that perturbation? That is the critical aspect here, right? And it's it helps us, and it's a drawback if you want to discuss more technically. Perturbations are not necessarily stable. There might be multiple thetas, right? So we can discuss that offline. But why do we do it? So what you see here, it's the convex envelope over calligraphic y, so over the solution space. So basically the points you see here are potential solutions that we will get out of the combinatorial layer, right? So the algorithm, we are linear in G, so we will always be pushed to the border. So we will end up in one of those things, right? So the red circle, red square, would be one solution for some theta that we get out of it. So the blue hexagon, think about the blue hexagon, about us training that pipeline, doing some gradient descent algorithm to parameterize the theta. So what we will see is we will not see a single solution, a single red square, but we will see an expectation over those solutions, which as it is an expectation that is slightly perturbed, will be pushed inside of that convex envelope, right? And if then you sketch the loss for the convex cone, what you see is that the inside, including the border of this loss, is 0. If you use the loss function, that doesn't have the perturbation, right? And this is a problem because I will end up somewhere here with my blue hexagon. I want to improve on phi such that I end up somewhere here. So if I see a 0 gradient on the loss, I will never improve, right? But if you add a perturbation, so a small Gaussian perturbation to that loss, then your loss gradient will change. So here was the border, it's no longer 0. And even here, it's no longer 0. So it's only 0 if you push very much into the middle of that cone. But that doesn't matter, right? That's a well-defined gradient because it's somewhere 0 and not 0 on the border where I want to end up and on the way there and on the way up. Right, so this is, we can improve on this color scheme, I agree, right? So the dark blue and the blue gradient is not ideal. But you get a non-zero gradient also inside the cone, and this helps you to get a stable gradient during training. And this is why you need the perturbation if you want to visualize it into it.
Your gradient is never.
Sorry?
It looks like you put twice the same people.
No, here it's all dark blue until here.
Ah, okay.
Which is you have a 0 gradient.
Okay, it's totally dark. Yes.
Yeah,
okay.
yeah.
It's not very easy to see.
No, it's a different one. So it's getting non-zero here and also inside. But yeah, depending on the beamer, so we could choose a better color scheme. I agree on that one.
Question? Here during training, your path of the gradient never 0. Is it always the case by training?
Yeah, there's some point in the middle of the code that is 0, but you will not end up there, or you're very unlikely.
Okay, you can.
Theoretically, you can if you. There's always a corner case, but by something over the solutions that are on the corners of the envelope, it's very unlikely that you end up here. Okay, so that's basically why we do that perturbation. And once you get this visualization and why it's important, you get the general idea of using that Fetchel-Young loss function. That's what it's called, and why you have to add the perturbation to derive a reasonable gradient for the product.
Sorry for asking.
No worries.
So your solutions are greedy, right? Because you are always choosing a theta given an x, but you want to take into account the future, right?
Greedy in what sense?
Like at a given time when you are making a decision, you were supposed to do a multi-stage problem. So where is the information from the forward?
The information from the forward perspective is hidden in the generation of the training data set. Because in the training data set, I solve the full day. And the slices are dependent on what happens in the slices afterwards. And since I'm imitating those slices, I implicitly account for the anticipation. Okay, so that's basically the methodology that we use, right? And then we compared it to different benchmarks. One would be like just greedy dispatching, lazy dispatching, random dispatching, standard rolling horizon approach, and Monte Carlo approach. And as an upper bound, just assuming full information, solving in hindsight and seeing how long, right? So this is basically what we compare to. We evaluated different request distributions. We report averages over 20 samples. We had 100 new requests per epoch. We set some decision time limits, right? So if we did the greedy, lazy, whatsoever strategies, we run the hybrid genetic search for 90 seconds afterwards. If we ran rolling horizon, we gave 600 seconds. If you ran Monte Carlo, we gave 5,400 seconds, right? So we even gave an unfair advantage to conventional approaches, if you want to see it like this. So we trained on 15 different distributions, 79 epochs, 50 new requests per epoch, 90-second decision time limit, as you also use it during testing. And this is what we get. So here you see the objective evaluated as a relative distance to the full information bound, right? And this is like, okay, we are 5 to 10% off the full information bound, but all the other approaches do worse, right? So an average gap that we obtain here in the end, if we crunch much more charts and all the figures, is that we get a gap of 5% to the anticipated strategy when using our pipeline. Whereas if you would do Monte Carlo, you get a 7% gap with 60 times the runtime, right? So we're not just better in terms of algorithmic performance, but also we are much more efficient in terms of runtime. And basically, with what I showed you so far is how we also won the Euro challenge. And we had like I don't remember, like 3% to the second place or something. So there were many approaches using DRL or some other stuff, and they didn't make it even close to what we got. So giving you some more results. So how do the results change if you vary the instance size in your training set? That was something that was rather surprising because we trained with 50 customers, but you had 100 customers released in each epoch during testing, right? So the question immediately was, okay, would we do better if you also train on 100 customers? And what we surprisingly saw is if you train on more or fewer customers, you don't do super bad, but you do worse. In the end, an intuition for this to explain it is, okay, if your instances get too small, then you fail to generalize, right? So then there's just not enough information in there to learn something proper. If your instances get too large, at some point, they do not provide enough structure to learn something meaningful, right? So both extremes are not good, whereas with some medium-sized instances, we observed the best results. We had different features, of course. This is a part in the paper where it's always written we had many meaningful features, right? And there's a messy appendix detailing them. So we had, let's say, model-free and model-aware features, right? And model-free features were like location, demand, time window, and so on. And model-aware features were observed distribution of travel times, slack times, and so on and so on. And the nice thing is that you see, okay, those are the performances. This is the one we get when we use all the features. With only model features, we get close. With only model-aware features, we are somewhat further away. But we benefit from both, right? So it's not that we cooked up a pipeline that in the end learned distributional information and did well. So we see a significant benefit from the model-free features, and those do not rely on distributional information, right? So that shows that we really learn some combinatorial aspects and dynamics in the problem that you could not retrieve just from a distribution approach. So this was one example.
Yes. I'm curious about something. Can you go back to the comparison between all the benchmarks?
Yeah. This one, yeah.
Yeah. So where does the length of the decision epic come from the organizer?
Yes.
Okay. What is the an epoch is what?
An epoch was 1 hour.
1 hour.
I think an epoch was 1 hour, and then you had a computation time limit on taking a decision of, I think, 2 minutes. I think in the first phase of the competition, like 3 or 4 minutes, and then it was decreased to 2 minutes.
I see. Just out of curiosity, did you by any chance train this thing in a shorter decision epic?
This one not,
fun to
but
know.
the next one. So this one not. We just stick to the competition. We were happy when we won it, and we rolled it up. But actually, before we jumped on this competition, we were already working on this one. So we were working on a structured learning pipeline for vehicle-to-request dispatching for autonomous mobility on demand, right? Where the slices are much smaller. So we don't talk about an hour. We talk about like 2 minutes, right? And there the hope also was that if it's just 2 minutes, but you inherit implicitly in your training data sets a structure of the full day, that you can take smart anticipative decisions, right? So I skip you another state space and action space. So the problem setting we just have is we make batch decisions, but the batch interval is like 1 minute or 2 minutes, and we have Uber whatsoever requests coming in. We have vehicles somewhere, and we dispatch vehicles to requests. And in the paper, we say it's that seems to be a Wi-Fi problem, not my email. Let me see.
It's working again.
It's working?
Slides is not shared anymore.
Yeah, that's
You need to reshare the slides.
so probably you disconnect, so you need to reconnect.
So there are many questions and sources of error that will excuse me for going over time. So,
Okay, we start to see us again.
are we back?
Yes.
Okay, let me close this one. Okay, I'm happy to see that not only in TU Munich the Wi-Fi is not working from time to time. So this is a problem that we have, right? And usually we say autonomous because A, it sells better for paper storytelling, and B, you can assume the drivers do what you want them to do, right? So you can erase some uncertainty.
That is the real.
The driver aspect. So we cook up a pipeline that is pretty similar to what I showed you before, just the combinatorial problem is a different one. And it's basically a dispatching graph that you can construct that constrains visibility, comprises feasibility constraints. It's acyclic, so you can solve the shortest path problem to get a dispatching sequence for the full day. And if you solve a k-disjoint shortest path problem, you can route a full fleet. And you can solve like 20,000 requests and 10,000 vehicles in less than 1 minute, right? Which is super nice because you can solve it optimally when you create your training instances. And then you use a pipeline very similar to what we had. We slice it, we train the predictor, and we run like a much smaller graph and a k-disjoint for this path when we do the online decision making. So if we do that, we tested different things. So basically what you see here, this is an animation of the full information bound. So there's no rebalancing because it's full information, so you directly know. Sampling is a classical model predictive control approach. So you sample from some distribution, potential future requests, take them into consideration when you dispatch in one time slice. And then we had our learning-based pipelines in two ways. One where we try to implicitly learn rebalancing, and one where for rebalancing we use the sampling that we would also use in MPC, but we still learn the prices for the dispatching. And you see differences in the policies. So what you see that if we learn the rebalancing, we rebalance much more. So the green dots are the rebalancing dots. We rebalance much more than in the other ones. Here, if we do MPC, we have too many red dots, so we have too much idling. So what worked best in the end was this one, where we learned the prices for dispatching, but still used some distributional information for the rebalancing, right? So that's what we did. And if you look at some more results charts, it's a comparison against greedy, which in those settings can be quite strong. What you see is in a realistic scenario, those of our learning-based pipelines beat greedy and also beat the MPC, which can even be worse than greedy, depending on the setting that you have. And this approach that combines the sampling and the learning works better, or work best out of those approaches. Right, but it's a second proof of concept on where using those pipelines works super well on solving some online decision-making problems with some combinatorial structure. So let's wrap that up briefly. Everybody who would now think, what is this guy presenting, would probably be right. Right? Because everything I presented to you so far is take whatever stochastic optimization book you like, you will find a page where it's written that you should not do it. Right? Because basically so far I told you it's really a great idea to imitate an anticipated policy in a multi-stage problem. In a classical sense, we've been taught that that should not be the case. And in fact, I showed you two examples where it works very well. You can also find examples where it doesn't work well, right? So there's a recent preprint of Thibault and some co-authors where they tried to use the approach that we had in those papers on an inventory routing problem, and where you will be worse than some other benchmarks or some advanced pipelines, right? So be careful if you apply this pipeline. It's sensitive to the policies that you imitate. It's sensitive to the learning algorithm. If you don't have a stable gradient, you're screwed. And you will find places where it does not work as good as it works in the two examples I showed you. So why is that? So if you think about it more from an MVP reinforcement learning perspective, what you would like to do is this, right? We would like to minimize some expectation over a loss, over some states, where the states are sampled from multiple policies, right? So basically, you are in a state, you have a transition to the next state, but it must not necessarily be the transition that follows the optimal policy, right? It can be some other transition, but it means a random behavior in the system. And that is what the first expression is telling us. This is what we would like to do, and this is what you can use to claim that imitating anticipated policies is a stupid idea. Right? What we do with what I showed you is this one, right? So all the states that we sample / how we construct our training data set stem from the delta star or pi star, whatever you want to call it, which is basically the optimal policies in hindsight of the data that was revealed, right? So we're pretty limited in reconstructing the transition function here because you always rely on the optimal policy. And there are cases where that works well, and there are cases where it does not work well, which means the learning algorithm, the way we designed it, it's somewhat weak, right? Or whatever you want to call that. It can work, but we can also be unlucky if the policies we imitate do not contain sufficiently many transitions. It will not work. Actually, when we did the NeurIPS challenge, Axel and I were expecting that it will not work when we proposed that to the students. Students were super happy that it immediately worked, but we were very surprised because our hunch was, okay, it will not work in the initial version, but then we will figure something out to make it work. But it immediately worked. In the AMOD setting, if you understand those data sets, there's a lot of autocorrelation in those data sets. If you talk to practitioners, they tell you, okay, the best rebalancing strategy in practice is if you have one request to send 2 vehicles. Right? So if you have a lot of autocorrelation, then there are not so many other transitions that you face, and then it works well. In the inventory routing, none of this is the case, and then it doesn't work well.
So your out-of-sample data is given to you, and that is highly correlated with what happened.
Exactly.
Okay.
Yeah, and then of course it works well. Right? Yeah. You can fix that. So there's something in machine learning which is called a dagger algorithm. I will not go into details, but refer you to Thibaut's new preprint if you're interested. Basically, what you can do, you can just enrich your training data set, right? So you take some transitions from the anticipated policies and cook up some other policies, take some more transitions. And then this is how you get the better performance here, where then the anticipated one doesn't really work, right? Thing is, if you go that route, so take the papers of structured learning, usually the selling argument you get is it's more sample efficient, right? So you once construct a training data set and then you can use it. So if we are now in this setting, we do dagger, where this is almost learning by experience, right? That is a similar principle to reinforcement learning, which is not sample efficient. Of course, you always trigger the next transition on the decision that you take, right? It's not the same, but it's a very similar logic once you end up doing dagger. Which is why I have 10 plus 10 minutes for questions and technical errors left, I would say, and then I may almost make it in time. The second half is more the DRL perspective, right? And for the DRL perspective, I will stick with the second example that we also had in the structured learning pipeline, right? So it's precisely the same, just that this time I want to cook up a pipeline that is not using structured learning to parameterize some predictor and then some combinatorial layer, but I want to use DRL with some combinatorial layer. So instead of using the pipeline that we had, we could also think about something like this, right? So this is basically pretty standard multi-agent soft actor critic architecture, right? You have an actor, you have agents with some shared parameters. There's a critic, there's a global state that is split again per agents, and that is fed back, right? So this is pretty standard. What is new is the gray box, right? So we didn't use soft actor critic to directly learn the dispatching decisions, but we said, okay, let's think about a DRL pipeline with a combinatorial element to take a global decision. So the combinatorial element that we use is just the bipartite matching, which is weighted, which just will assign vehicles to requests. And we maximize that matching and then get the best allocation. And then what, the question is, okay, if we put this into the DRL context, what would be a good predictor / DRL agent to give us the input for that matching? Right? And this is basically where the multi-agent setting comes from, because the agents that we train are vehicle to request combinations. So basically the agents will learn scores for vehicle to request combinations that we use as an input to the matching. Then we solve the bipartite matching, we get our dispatching, and we're done. If you do it this way, this is what you get. So again, New York data set. Remember, with the structured learning pipeline with the sampling, we had like over greedy 5 to 7% improvement, right? So what you see here is greedy is the baseline at 0%. Then the red one is multi-agent DRL with bipartite matching, no rebalancing. And then you almost learn greedy with some variation, right? The purple one is with rebalancing, but with a heuristic balancing. So similar to the structured learning pipeline using distributional information, which was the best performing one in the structured learning way, right? So we sample from that distribution and we try to rebalance vehicles proportional to the spread of that distribution, right? And then you get this one. And then here you already get something which is much more than 5 to 7%, right? Which is more like 15%. But you see that, okay, we did better than the state of the art because of autocorrelation. But also there you can reveal that you are suffering from not evaluating the right transitions, right? Because here we have learning by experience and we can improve even more. And then the interesting thing was, this is a version which is completely distribution free / model free. So there's no distributional heuristic for the rebalancing, but we implicitly learn the rebalancing. And here that works better, right? So as soon as you have a pipeline that explores sufficiently and models transitions correctly, then you also benefit from learning the rebalancing. So basically the effect that the rebalancing based on distributional knowledge worked best in the structured learning setting was because there we suffered from imitating based on the wrong transitions. If you want to connect the pieces between the two pipelines, right? So this is nice. Problem is, I'm neither advocating the structured learning pipeline nor the DRL pipeline, right? Otherwise, I would stop here. So if you go the DRL way, you will get different problems, right? One problem being scalability. So if you look on the details on the plots, here it says zones, right? It's no longer really explicitly modeling of requests, but you cut your map into zones to keep it somewhat tractable. So if your action spaces, which are usually discrete, get too large, you run into issues. And another issue is robustness, right? So if you look at the spreads here, there are quite some spreads. And also, if you have distribution shifts, then your policy can be quite sensitive, right? So which is why I will just point you to two things that we recently did on those two issues, one on scalability and one on robustness, right? So I will go away from those pipelines, but you can use all of what I show you now in those pipelines where you have a DRL element for the learning, right? But I will just skip it for the sake of being concise and then focusing on some elements. So the first one I will briefly show you is, okay, if you do DRL, how can you scale to very large action spaces? And by very large, I don't mean the very large that the DRL control people mean, which is like 10 to the power of 3 or 10 to the power of 6, but I mean like 10 to the power of 70, right? So you solve some combinatorial multi-stage problem where your action space goes exponentially, and then you're screwed, right? So it's a different magnitudes that you're talking about. So I look at such a problem. It's some NDP, it's sequential decision making. It's a discrete action space. There's a state space, there's an action space, there's a reward function, there are some transition dynamics, right? And what I'm interested in is, okay, with the motivation that I want to use DRL for contextual decision making in an operations research context, which means I will end up with a discrete action space that is combinatorial and large. How can I get something stable, right? And I will limit the thing that we did to regularly structured action spaces, which basically means, well, you can somehow describe that action space in some hypercube or some hyperrectangle, right? So that in between the discrete values of the actions, there's some distance, and it can be the same one in multiple directions. It can be different ones in multiple directions. It doesn't matter. But to make that efficient, so it would also work in an irregular case, but it would be less efficient, right? And you will see later in 2 slides why. So to make it super efficient, it's nice if your action space is somewhat structured. So what is the idea then? Okay. We are screwed if we learn a large discrete space. We have some policy objective function J, where we usually try to maximize the expectation over the discounted rewards, like the Q values of our state action pairs, right? So that's what we do. Gamma is the discount factor. Let's take an actor-critic algorithm because it's the most stable one, right? If you go more basic, you will not converge. If you go PPO, you go computationally heavy, data hungry. So we just stay with actor-critic. So we try to encode a neural network that encodes our policy and a critic network that learns our Q function, right? Then if A is discrete, our pi, so the neural networks that encodes our policy, contains the cardinality of A output nodes, which is not so nice, right? So that gets a rather large thing. And then we have the problem I already mentioned, is that the cardinality of A grows exponentially with the state dimension. If we look at inventory management, job shop scheduling, take whatever optimization problem you like, right? And we see this exponential growth, and this is not good. So if you would like to train that, we would need a vast amount of training data, a vast amount of exploration to learn something meaningful, and easily end up in a case that it's just not tractable, even for 10 to the power of 3 or 2, right? So it's not 10 to the power of 70. So we want to go somewhere very different. The nice thing here is, I'll show you how to do that with something that we know in OR for 40, 50 years. So what we do is the following. It's bad to learn in a discrete space, or difficult. So what I want to do is, okay, I will just learn in a continuous space. I learn in some continuous space, with some continuous action, and then I will map that to my discrete space, right? So gradient descent algorithm on a continuous space, it's super stable, super nice. So this method succeeds or fails with me finding a good mapping from the continuous action to the discrete action. And people tried that before by exploring a KNN neighborhood from the continuous one to the discrete one, learning some embedding, which involves enumerating everything up front, which doesn't solve the problem, right? So there have been many approaches on making that mapping. None of them really working well. Let me put it like that. Not working at all. So you will find problems where it works, but not scaling to the dimensions to which we want to scale, right? So what I will do instead is that I will try to measure similarity between actions, right? And you can do that by defining some Lipschitz constant that satisfies those properties, so that the distance between the Q values is smaller than the Lipschitz constant times the distance between the actions. And then you can show that this suffices to really evaluate some kind of cohesion between the actions, right? And then you crunch some more math and some more theorems. And what you can up with is what hides behind B and C is you just do a local search with some simulated and leading acceptance. So you start with some mapping. You will use the similarity measure to create a limited neighborhood on which you evaluate if you find a discrete action with a better Q value. Then you evaluate that neighborhood, stop with the best one you found, go back, create, again with the similarity measure, the neighborhood on that best found, and try again. And by that, you will just walk a bit further in this mapping from continuous to discrete compared to any KNN or some other deterministic mapping or some embedding, right? And in the end, we do that with something that we used in OR for 40 years, just in a very different context. I don't know what was first.
How do you parameterize your simulating annealing? Usually the typical scheme is to decrease the operator. Yeah, imagine you don't use it as something that you want to converge. So what's your gamma?
So the parameters, I would have to look it up. So I don't know them out of my head. It's actually something we discussed, and actually I was the co-author who said we are good with only local search and without simulated annealing, but we tested both and we see a better performance. And so the reason is that in the end, to find corner cases, so it is a neighborhood you define, not often, but sometimes you have corner cases, but the best improving action, it's just a bit more outside so that you really profit from jumping out of the local improvements.
Why is it sufficient to only explore the limited small neighborhoods? You said that you will only look at the neighboring actions.
Yeah, but you do it iteratively.
Okay.
So you define a small one, which is much more easily to search in. Yeah. You jump to the best point in the small one, you find another small one. If you would do it once, you would get a similar result to the other branches. Okay, so that's basically what we do. And I just quickly pitch you some results, right? So we evaluated this on a drop shop scheduling problem and on an inventory replenishment problem, where you have multiple order up to levels, multiple items that you want to reorder, classical holding backlog costs and so on, and some link costs once you place an order and stuff like that, right? So I will not go into the details for the sake of time because there's one more thing I want to talk about. But this is what you get, right? So here what you see, this is vanilla actor critique, right? No attempt to scale in any sense. This is a learned action representation. So this is basically learning embeddings and try to map up front. This is the KNN neighborhoods. That is some min-max mapping from continuous to discrete. And then you have the heuristic we cooked up once without simulated annealing and once with simulated annealing. So first observation, there's no orange, green, or purple line on any of the charts, which means that those methods do not even scale to the size of the action space that we have here, right? So they didn't even converge. And then for the job shop scheduling, we talk about 10 to the power of 10 actions. And what we see is that the min-max mapping works somehow. But if we look at what we achieve by smartly searching the neighborhood, is much better, right? And this is the one without simulated annealing, where we are already better, but the deviation in corridors overlap, so we are not dominating. But once you activate the simulated annealing to have the effect that I briefly sketched there by jumping out to catch those rarely but existing moves that are a bit further away, you dominate and you get a much better performance, right? And we see the same on the inventory case where we have 67 to the power of 20 and 67 to the power of 40 is a similar behavior, just a bit more clearer because already the DNC without simulated annealing outperforms the only other methods that scales at all, right? So I was very happy with this paper because I think it's something we see these days quite often, that we in OR have problems where the ML guys have solutions that we just don't know, but also the other way around, right? And this was the other way around. By just cooking up a simulated annealing guided local search, we could scale to much larger action spaces and solve those problems. So the last one, and I will do it very briefly to not stress anybody's patience too much. Marius is giving me nice hand signs to say hello, right? Is the robustness, right? So robustness under distribution shifts. So basically what I'm interested in, let's take some stylized environment, some pickup and delivery problem. So some item pops up, I want to pick it up and drop it somewhere. I will train that with ERL on some distribution of demand, which might be gradient 1. Right, but what could happen in practice is there's endogenous uncertainty or whatsoever, or just a shift in my distribution. So that's that I execute my policy in the end on gradient 4, gradient 9, gradient 5, whatsoever. And the question is, can I train a policy that also performs well on those other gradients without sacrificing too much performance on my training gradient? Right? And if you think about it, there are 3 ways to do it. One would be you just remember what everybody does in supervised learning, which is manipulating training data, right? You do image detection or whatsoever. You want to get robust, you manipulate training data. So we could do the same here, right? We could just overlay the gradient of the distribution that we have with some uniform gradient or some other gradient to a certain percentage share and get noisy training data. And if we perform well on this, we should be more robust. The second one, and this is what is often done, we could ignore the problem. Right? We could just say we use soft actor critic. Soft actor critic has an entropy term, entropy regularization, increases robustness. We can show that numerically and theoretically, so we're done. So we don't have robustness issues in deep reinforcement learning. Or we could take the last one, which is a principled approach, where we say, okay, we want to explicitly consider some kind of risk measure to steer robustness, right? If we are risk averse or not. This would be the vanilla soft actor critic. You maximize your expectation over reward plus some entropy regularization, right? So what we wanted to do here is different. We want to consider an entropic risk measure, right? Which is basically the expectation over the reward plus my beta times the variance of my reward, which is where I trigger the robustness plus some higher order terms. Right, and now I will skip the rest of the slides to make it by the end of the hour, right? So this equals that, which gives you a maximization over a policy over this longer term here. And then the question, if you want to do deep reinforcement learning there, is can you derive a Bellman equation of this form where you still sample an expectation of the probabilities from your policy over the state action pairs to which you transition? And the mathematical answer is, unfortunately, you cannot do it because we're having a logarithm here, right? So building an unbiased sample over a logarithm is a difficult thing to do. It's actually a thing you cannot do, which is why you cannot continue directly with the risk measure you want to consider. But you can show that you can define a surrogate Q function where you just have the Q function that you had here in the exponent of an E function. And for this one, you can prove that you can derive a working Bellman equation. And then you will encounter some more problems because it will be not numerically stable. There's a log sum X structure that you want to avoid and so on and so on. So there are some more proofs and discussions on how to really learn that in the paper, but I will skip it here because I'm having 60 seconds left, right? Which brings me just to the results slide. So what you see is quite interesting, which is you see the performance on the gradient on which you trained and the performance on all the other gradients that I showed you in the beginning, right? So manipulating the training data, no matter how much you manipulate it, you get a somewhat reasonable behavior, but a bad behavior on the other gradients. So you do not really succeed in increasing robustness, right? Whereas for entropy regularization, this is what you get. So with an increasing importance of the regularization term, you will decrease on the performance of the gradient on which you train, but you will increase on robustness, right? And for the principled approach, we stay stable and better on the gradient one and get also like some robustness on the other gradients. Right, so if you would like to evaluate it, you do not evaluate all the points. You would do some hyperparameter fitting, right? So for entropy, you would take this point, and so on and so on, right? So you would pick one parameter selection. And then it's tough to take a decision because, I mean, we can agree on manipulating training data being worse than entropy regularization or risk sensitivity in a principled way. But then we would have a decision problem, right? Then the question is, okay, how to decide now? Is it better to be good on gradient one or on the other ones and so on and so on? So what we in the end did is that we took a convex combination, a weighted average, just saying, okay, tell me how important it is for you to be good on the training gradient, which will most likely happen, and how important it is for you to be good on the other gradients. And if you take this weighted sum to evaluate performance, what you see is if at least 37% of your objectives are related to being good on the original gradient, where I would argue, even as a risk-averse decision maker, it will be at minimum 50%, right? And then you want to be robust in some other cases. Then the principled approach is better and gives you better performance, right? If you just care about the other gradients, then you're better off with entropy regularization, but well, then you're just minimizing the worst case. Right? Okay, do I have 20 more seconds? Perfect. So with 20 more seconds to wrap up, right? So I gave you many different pointers that might be interesting, and I'm happy to hear your views on those things. But if you want to take some measures from this, I think one thing that we saw is that independent of the learning architecture that we use, if you're facing combinatorial, contextual, multi-stage problems, it helps to have a combinatorial layer, right? Because even if it's an online problem, even if it's dynamic and there's uncertainty, there's some combinatorial structures. It just helps to exploit it, and it's easier to exploit it if you have a combinatorial algorithm inside. And that helped in the structured learning pipelines and in the DRL pipelines, right? No matter what you like better, you will definitely be better off by having a combinatorial layer. What we also saw in the structured learning part is that, well, imitating anticipative policies can work very well, right? Even on a single scenario, if the policies we imitate are containing the right transitions. It does not always work, but it can work. And if it works, it's just a big computational advantage, right? So don't take me wrong and say, this guy said I should always do it. That's not what I'm saying, but if you have a good hunch that it works, or it's a simple proof of concept, and often you can already improve over a conventional state of the art. Let's put it like that. Then DRL pipelines can be scalable, right? If you have the right mapping. So the argument we need to go structured learning because DRL doesn't scale. Well, take the ICLR paper and it scales, right? So that does no longer hold. And they can also be principled in steering robustness, where I'm not claiming it's not possible in the structured learning pipelines, but it hasn't been done yet, right? So if you're looking for an exciting and probably a hard research topic, breaking your mind on how to create a robust structured learning pipeline, I think it's an interesting topic, but it's also topics that you will not solve tomorrow morning, right? I think it requires a bit of math and a lot of thinking. With that, I'm finished. There are probably 10 more takeaways, but if I were to also list them, I would definitely run out of time. So thank you for being here. Thank you for listening, and I'm happy to answer any questions.